Hello everyone, my name is Patrick. Last year I was responsible for designing the steering system. This year I'm responsible for designing the suspension. So basically, if you have any questions along the presentation, really don't hesitate to just raise your hand and ask your question. So first of all, what is the purpose of the steering system? It's to allow the driver to control the car, to easily control the direction of the car. In our case, it's obviously to make the car go as fast as possible around the track in competitions, and not so much for the style. So basically my presentation will be split in three main parts. I will first go over some basic vehicle dynamics concepts, how force is transmitted to the steering system. Then I will follow with ergonomics, describing certain factors that guide the mechanical design. And then I will follow with the mechanical design. Ergonomics and mechanical design really go hand in hand. It's basically a compromise between both sometimes. So I'll go over these. And obviously, design is guided also by the FCA rules, which basically don't allow you to do certain things, so you have to design around that. So first of all, the steering ratio. Steering ratio is basically the ratio of rotation of the steering wheel versus the wheels. So basically, an easy way to represent that and show how it's calculated is basically the distance between the axis of rotation of your front wheels to the point where the clevis mounts, the clevis, which is what moves sideways. The ratio of the length L1 to the length L2, which is basically the radius of the pinion. So basically L1 divided by L2 will give you your ratio, which is fairly constant throughout the range. It's not exactly that, but it's fairly close. So basically, if you have a steering ratio equal to 6, that means that you will input 6 degrees at the steering wheel, and you'll get 1 degree at the wheel. So the faster your ratio is, so the higher the number is, that means that obviously the lower the ratio is, I made a mistake on there, the lower your ratio, for example, a steering ratio of 4, that will mean that you will have to input less at the steering wheel, and you get more output at the wheels. And that also, it first affects how quick your steering is, and also affects the steering feedback that you get. Because if your steering ratio is faster, you will basically have a larger force feedback through the column. So basically, the force that are transmitted through the steering system are guided by two things. The Fy, which is the lateral force generated by a tire, and Mz, which is the moment generated around an axis normal to the ground, so pointing upwards in that case. So basically, you want the steering feedback to be to help the driver get a feel of the front axle grip. So basically, if you're driving the car and the steering wheel has no feedback at all, you will not get a feeling of if the front tires are losing grip, are you going faster in the corner or not. So you basically want that feeling to be represented for the driver to feel how close he is to the maximum lateral acceleration the car can achieve. So basically, Mz, the moment around the axis normal to the ground, is always present and will not be affected by geometric positioning of your points holding your wheel. So basically what you can play with is the lateral force. That lateral force basically, in a case where you would have the point number 4 and 5 here are the points around which your wheel pivots. If that axle was to be in the middle of the tire and straight up, your lateral force is always applied at the center of the contact patch. So if you have a force times the distance, which in this case equals 0 from the center of the tire, this lateral force will basically not transmit any feedback through the steering wheel. So if your axis of rotation of the wheel was straight up, that Fy would have no effect whatsoever on your steering feedback. So on one side, this would allow the driver to have a less force to input through the steering wheel. So on this side, that would be good. However, in the case where the lateral force Fy would not affect the feedback, only Mz would be what the driver feels. In this case, Mz will the feedback of the MZ will peak before the FY. What that means basically is the driver will feel the highest feedback at the steering wheel before he reaches the maximum lateral acceleration, FY, that the car can achieve. So that can be misleading for the driver if he doesn't have much experience, in the sense that the driver might think from the feedback that peaks and then falls off after the steering wheel gets softer, that he thinks that the car is losing grip, so he should not go further, which might not be the case. So that is the reason why you want the FY to the lateral force to take a portion of the feedback that you feel in the steering system. So basically how you do that is by inclining that axis and offsetting frontwards or backwards. All that does is if you take the projection of a line that's passing through these 2 points and you project it on the ground, and then you simply measure the distance from the projection of that line on the ground to the center of the contact patch, that is what you call the mechanical trail. So the mechanical trail is simply a length measurement, and you times that the lateral force, which is applied at the center of the contact patch. So basically, you have a force applied at a certain distance from the axis of rotation, which gives you a moment. So basically, adding that, your total moment generated by the tire will be equal to Fy, the lateral force, times the mechanical trail, plus the moment. So by adding the lateral force in the equation, you will basically give the driver a more accurate feel of what is the maximum lateral acceleration, because you will correlate basically the feeling of the steering wheel, which will have the highest feedback very close to the maximum lateral acceleration. So you play with these. Obviously there's a lot of different opinion on that subject. Some people might go with a very little mechanical trail to have a very light steering wheel. If the driver is really experienced with the car and used to it, he will probably be able to reach the maximum lateral acceleration, even though the feeling at the steering wheel is not exactly what the lateral acceleration represents. So basically, that's how we calculate it. So now moving on to ergonomics. 3 main parameters. Angle of the steering wheel. What I mean by that is simply, if you look at side view from the car, how tilted is the steering wheel? So basically we got 2 opposites. Vertical right here, or like a tractor wheel, like this. This will affect, obviously, how the driver's hand moves. So basically, the closer to being parallel with the driver's chest, that will make it easier for the driver to have a wider range of motion without having to change the position of your hand on the steering wheel. Basically, if you had a steering wheel like this, you can imagine that as steering the wheel, one arm will stretch. The position will quickly become uncomfortable for the driver. The distance from the steering wheel to the driver's chest is also another factor. This will highly affect the elbow room that you get. Obviously, we try to design the lightest car, so it's usually pretty small. The cockpit is right next to the driver's elbows. So if your steering wheel is really close, when you steer, you're very likely to hit the side of the cockpit, which will probably be uncomfortable for the driver. So by putting the steering wheel farther away, your elbows do not necessarily stick out. So you need a bit less elbow room, and it makes it more comfortable. After that, range of motion is sort of included in 2 other parameters. It's dependent on the ratio that you have that I explained. So basically how many degrees at the steering wheel you have to input to get X degrees at the wheels. And to determine the angle you need at the wheels, this is simply determined by the tightest corner the car will have to go around on a racetrack, which is set by the FSC rules, outside diameter of 9 meters. So you can basically compute it from that. On the mechanical design side of the column, there are a couple options. Basically, this is obviously heavily dependent on the ergonomics. For example, I'll start off with the example of a straight column. Here we got the McGill Baja Racing Team steering design this year. Their column, if you can see it here, is straight. There is no U-joint, there's no bevel gear to change the angle of the column. This was chosen for simplicity. Basically, it was more important for them to have a lighter system, simpler system, rather than having the steering wheel tilted this way and having a U-joint or another system that would allow the column to connect the steering wheel and the rack. So basically, in our case, we prize more the driver's position, and driver's position is also quite different. We're more reclined, lower, so the steering wheel has to be tilted towards the driver for the other ergonomics reasons that I explained. So basically, the system that we use on MRT15, the car that competed this season, is basically a system composed of two U-joints. U-joints are simply links that are used to transmit rotary motion with two axes coming not in a straight line. So basically, most typical U-joints have a maximum angle of 35 degrees measured from a straight line. Basically, you can go maximum 35 degrees in any direction, whether it be downward, upward, sideways. Obviously, in our case, it's downward. So basically, you really start from the positioning of your steering wheel, how far it is, how high it is, what's the angle in between your rack, and then from there you determine how many angles your column has to go down, and from there you can select whether you use U-joints, which is what we use, simple to use, simple to assemble, so those are the main reasons why we chose it, and it's fairly light. You also can design a system of a bevel gearbox. This is basically just a set of gears that if you design them yourselves, you can basically make them coincide at any angle you want. 90-degree angle is obviously a common setup, so you can also use that. However, this requires quite a lot more efforts put in the design to make your own set of gears, design the housing around it, so it requires more time, but allows for a bit more flexibility, and is also quite different from any conventional steering system. So it's definitely an option. However, it requires more thought and analysis put into it in order to have something that works well and that's reliable. In terms of steering wheel, the option we've been going with for the past 2 or 3 years is a simple sandwich panel of carbon fiber and core. This picture has been taken from Andy's PowerPoint last week. Same principle. If you had only layers of carbon fiber without any core material, your stiffness would be relatively low compared to having core in the middle, which is very light. So your weight is only increased by a couple %, whereas your stiffness doubles, triples, depending on how thick your core is. So this allows for basically a very simple part to make. It's only a couple layers of carbon fiber, core, and the same number of layers on the other side. And then this can be water jet to cut out the profile. And then we use rapid prototype handles to basically stick that to the cutout shape of the steering wheel. Following with the steering rack. So basically, from the steering wheel, you have the column that connects to the rack, and then you have to transfer that rotary motion into a linear motion, which is most commonly you use a rack and pinion to transfer that rotary motion in that pinion to a linear motion of the rack. So that's basically a pretty common system. And then we use a housing made of aluminum that is CNC because obviously when you have a set of gears, it's one of the critical factors. Obviously there's the preliminary design of how the gear is made, but the positioning of the two main parts together is really, really important in order to have an easy actuation, no bogging. It doesn't get harder throughout the range of motion of the steering wheel, and also minimize the backlash. Backlash being, again, the blade that you got side to side when changing directions. So basically the CNC aluminum housing allows for a pretty accurate mounting. However, we also included a system of off-centrics. I don't know if you can see it very clearly, but these off-centrics right here is basically a piece of aluminum in which a bushing of bronze is inserted. And basically the thickness of the aluminum is thinner here and thicker here. It's not by a lot, it's 30 thousandths of an inch. That's really small, you can barely see it. However, that allows, that part goes right here and it basically adjusts the distance between the pinion and the rack. So that allows you to make a very fine adjustment between the distance of the rack and the pinion. So that is simply to minimize the backlash and not have any balking in the system. So that's basically how the lower part of the steering system is assembled. So this is all I had. Any questions?
How does the angle between points 4 and 5 affect how the steering feels, or why would you change that angle?
Well, the mechanical trail here is affected by two sort of geometrical constraints. It's both the angle and the offset of that point. So there's not only that, but there's only other suspension kinematics considerations. But if we only consider steering, what will affect the mechanical trail, which is the only factor affected by those 2 points, will be by changing what we call the kingpin inclination, or the caster angle, and the offset basically, which will make that bigger or larger. And varying the mechanical trail will basically vary the proportion of, well, the proportion of the contribution of Fy to the total moment generated by the tire.
So why wouldn't you just have 2 straight points that are forward of your contact bench?
This is dependent on other suspension parameters, such as, I guess, anti-dive, how your suspension reacts in other cases, but that's affecting general suspension parameters of the car, but not specifically steering.
So are you concerned that the wheels become cambered when you steer?
Yes, however, I did not plan my presentation to that extent.
Okay.
But yes, this will obviously, as your wheel turns around it, you will have more camber, but this is one other parameter that can be simulated to, depending how your tire behaves. Will it gain more grip with camber? Will it have less grip with camber? So basically we use OptimumK, that's a simulation software that simulates the geometry of the suspension, so you can simulate when the wheels will have a 30-degree angle, how many degrees of camber will I have, and then couple that with the tire model that we have, we can see how the tire reacts to such a positioning, and then we can see if it's better or not.
So what's camber?
Camber? It's basically, if you're sitting in the car, it's the angle of the wheels inward. Basically, as you turn, obviously, well, it's always, like, I guess, normal to the sidewall of the tire. But that is camber. And toe would be the other angle. Back towards you. Yep.
I know it wasn't included, but do you know how power steering works?
Yeah. Basically, power steering is just hydraulically actuated. It's basically, that's more in just bigger cars, because in our case, our car is pretty light. So just by adjusting the mechanical trail, and you can get a steering feedback that is fairly good. It is higher, the steering feedback in our car is higher than a normal car would be. The reason for that is, I guess, getting a more accurate feel, because in a car, you know, it's very, very soft with power steering, you get barely no feedback. So it's pretty hard to feel, it's harder to feel at least, when your car loses grip, whereas in a race car, you want really to feel more of the car, but not too much, obviously, because the driver can get tired and then thus less accurate. But power steering is basically a hydraulic system that contributes to the force either way it goes. So it just makes your housing for the steering rack, in my opinion, a lot more complicated. Yep.
So this is a bit off topic, but so you said that for track racing you want a higher feedback. So for something like rally racing, would there be lower feedback then for compared to a normal car, or Jim Connolly showed in the meeting?
Yep. Honestly, the feedback is, to some extent, it's a personal preference. To some extent, it's also dependent, obviously, on the surface you race on.
Right.
It's dependent on how the tires react. But in any case, I don't have any experience in rally, but it could be different for multiple reasons. In case where you drift in Gymkhana, you might not want to have a heavy steering because you're not really looking for the peak lateral acceleration. You're just looking for putting those wheels to aim the nose of the car where they belong, and you control the car differently. But it's really a case-by-case analysis that you go ahead and see what will make the car the fastest, basically. Okay. So it's basically, the steering system is a system that's made to make the driver able to control the car as easily as possible and just forget about it, you know, and just thinking about what he wants to do, and the car does it. So
Okay, so like a large part would be up to driver preference then.
yes,
Okay.
when you get like professional drivers and professional racing series, then a lot of it is driver preference. Some will prefer some parameters more or not. So what makes them the fastest will be the best setup. Questions?
Have we ever tested how tired the drivers can get to try to decide their steering ratio?
We did not test that on track, however, we experienced a moment where basically behind here, we don't see it on the picture, but there's a set screw that is sort of a safety thing that if you can figure that this rack goes into here and the pinion here goes into that interface. So basically the set screw on the other side prevents the rack from deflecting too much, and we had this set screw too tight, so it was putting pressure on the rack, so there was a lot of friction generated. So basically it was a lot harder for the driver to steer the wheel, and especially in the slaloms, because if you're static, the friction on that is static, so it doesn't really increase much the force the driver has to put in. However, when you're in slaloms, you have to put a lot more force back and forth. So in that case, that was where I'm driving. He definitely noticed that the steering was a lot heavier, and it was too hard. It made him tired to the extent where he was getting a bit slower, and it was harder for him to aim accurately in the corner.